Okay, very good. Now, so we want to get the formula for this function, right? We want to be able to express this function in terms of the Heaviside function. Well, it's the negative of the Heaviside function, except it's 0 all the way up to 1, right?
Right.
So if you take the negative of the Heaviside function and shift it 1 unit in the positive horizontal direction,
Right.
okay, you get it. So that this function must be negative h of t minus 1. Okay? Now the next thing I'm going to ask you to think about and see if you can do this for homework, because we're just about out of time. We're not going to get to the last problem, but we can pick up with that. That's just partial fractions. Very simple. So I'll say decompose that third one into partial fractions and see if you can figure out what that's the Laplace transform of. I'll probably put a few hints. Okay? But for right now, here's what we want. We want a function I described in words that goes from positive 1 to negative 1, or from, actually, this is a voltage function, okay? And what we want is our voltage function. And we'll let the voltage function start at 0. It goes this way, and this way, and this way, and this way, and this way. Forever, or until we decide to stop cranking the generator. Okay? Now you know you've produced this, you've observed what happens to a capacitor. But we also observed that if you have a sine function, you can solve the differential equation very easily, right? If you have this function, you can't. You can just say, well, it's going to exponentially approach this, it's going to exponentially approach this, and you don't really know what's going to happen ultimately. Okay? Now, you could work out the ultimate solution, but you wouldn't have a good transient solution. Okay? You wouldn't know when you wouldn't know exactly when things happen. Okay? So that's just background with what you've seen in physics. Okay? But you have V here, negative V here, and period T, meaning a period is where you go from here to here and then back to where you started, right? So at time T, it's back here. At time 2T, it's down here. You really don't have to worry about which part of the interval is open, which part is closed. You can make your own choice. Okay? So you got this step function driving a circuit. Okay? So you'd have like your dq dt, okay? And your q over c and all that, and it's being driven by this, so you have a non-homogeneous function, and it's this function, and it can be written in terms of Heaviside functions. But it's going to be an infinite sum. So, okay. Transform Heaviside function. I would start by just, well, you can get this one, right? You just adapt what we did here. Right. And then we can get 2 steps. You just adapt what we did here, but you got to add 3 functions, okay? And then you get a pattern. And then you ask yourself, well, what's the infinite series? But it turns out it doesn't matter, because once we have one period, we've got a simple formula for the Laplace transform of the function forever. Okay? And we, talk about that next time. But this is where the Laplace transform gets really useful. There are many other uses. You can translate, it turns out, a differential equation to an algebraic equation in S. Differential equation in T becomes an algebraic equation in S. You do a little algebra, usually some partial fractions. Not difficult. I mean, yeah, it can get really difficult, but, But you find your transform solution, okay? And then you just transform that back into function space. You find what function has that transform. Now, the third problem, I ask you to do the partial fraction decomposition. So I ask what function has a transform of s squared over quantity s squared minus 5s plus 6. Easily factor the denominator, do the partial fractions. And then we'll talk about, and then think about, okay, you're going to get two terms in the partial fractions. Okay, it's perfectly okay to look at this table of transforms and see if you can figure out what those functions are. What functions would give you those two transforms. Okay? So the more that you can do for next time, of course it's short time between Tuesday and Thursday, the better off you'll be, but at least do the partial fractions so we don't have to stumble over that. And do what you can with this one. At least get this, and then get this. And then if you see what goes next, go a couple more steps, you might see a pattern. Probably would. We saw the previous pattern.